transitional phase, linking dense, star-forming galaxies to the earliest massive black holes. In this video, we'll look at what was discovered, why these objects matter for understanding galaxy evolution, and what comes next in this line of research. Let's get started. The first detection of little red dots came in late 2022, during James Webb Space Telescope's early deep field surveys. These sources appeared at high redshifts between 4 and 8, meaning we're seeing them as they existed just 600 million to 1.5 billion years after the Big Bang. Their physical properties stood out immediately. They were extremely small, often just a few hundred light years across, far more compact than typical early galaxies. They also appeared very red in James Webb Space Telescope's infrared filters, pointing to either heavy dust or energetic processes in their cores. Two main interpretations emerged. 1. Stellar-only model. These dots could be ultra-compact, dusty star-forming galaxies, where intense stellar activity is responsible for their red color and brightness. Such systems would represent concentrated starbursts in the young universe. 2. MB-H+ galaxy model. The alternative is that they're early active galactic nuclei, systems hosting massive black holes, whose accretion activity gives them their distinctive spectral features. Spectroscopic data from James Webb Space Telescope added complexity. Many little red dots showed broad Balmer emission lines, indicating very high internal velocities. This suggested either intense gravitational binding or black hole activity, but they didn't fit cleanly into known categories. For example, if they were powered by black holes, astronomers would expect significant X-ray emission, but most of these objects showed little or none. And if they were just starbursts, the extreme velocity dispersions would be difficult to sustain in purely stellar systems. Their unusual combination of small size, red color, high velocities, and weak X-rays pointed to something in between: galaxies caught in the middle of a transformation. Understanding these little red dots matters because they offer a glimpse into how the first galaxies and black holes formed. This is one of the most active areas of cosmology right now: how structure emerged in the universe's first billion years. The stellar-only interpretation describes little red dots as early galaxies undergoing intense star formation in extremely compact regions. If that's correct, then star formation in the early universe was much more concentrated and rapid than current models suggest. These systems could be the earliest building blocks of more massive galaxies. The MB-H+ galaxy interpretation, on the other hand, focuses on the broad emission lines as signatures of black hole accretion. This would mean some of these galaxies already contained black holes that were unusually massive compared to their hosts, around 10% of the total galactic mass, compared to about 0.1% in the modern universe. That would offer a direct clue to how black holes grew so fast in the early cosmic timeline. Both scenarios explain part of the data, but not all of it. The lack of strong X-ray signatures is particularly challenging for the AGN interpretation, while the extreme velocity dispersions are difficult to reconcile with a purely stellar system. This is where the new evolutionary model proposed by Escala's team comes in. Instead of treating the two explanations as competing, they propose they're two stages of the same process. First, these systems form as extremely dense, star-dominated galaxies. Over time, the high central densities cause their inner regions to collapse. This collapse seeds or rapidly grows massive black holes at their centers. Eventually, these black holes ignite, turning the objects into active nuclei. This model explains several observations at once. The absence of strong X-rays fits with the idea that many little red dots are caught in their pre-AGN stage, before the black hole fully lights up. Their scarcity at lower redshifts also fits this picture. This is a short-lived phase, visible only during early cosmic epochs. By connecting the stellar-only and MB-H scenarios into a single evolutionary track, this theory transforms little red dots from outliers into expected waypoints in early galaxy evolution. If this interpretation holds, little red dots give us a direct observational window into the formation of massive black holes in the young universe. This helps address one of astronomy's biggest open questions: how did black holes reach billions of solar masses so early? These objects could represent the earliest seeds of the supermassive black holes we see in mature galaxies today. If black hole growth indeed began in such ultra-dense stellar environments, then early black holes may have formed far more efficiently than previously assumed. That would explain their rapid emergence without requiring exotic mechanisms. Little red dots also challenge how we model the co-evolution of galaxies and black holes. In the local universe, the mass of a central black hole scales closely with the mass of its host galaxy. If, in the early universe, black holes were proportionally much more massive, it means the relationship between galaxies and their central black holes evolved over time. Early black holes may have shaped their host galaxies rather than growing in parallel with them. This has implications for how we interpret other faint, high redshift infrared sources. Some may not be simple starbursts, but rather pre-AGN systems, where a black hole is in the process of forming but not yet fully active. Recognizing this transitional stage can refine how astronomers classify early galaxies and how they model their impact on cosmic evolution. To test these ideas, astronomers are focusing on several observational strategies. Deep X-ray observations can detect weak accretion signals, confirming or ruling out early AGN activity in some little red dots. Infrared spectroscopy will better constrain their velocity dispersions, gas content, and stellar masses. Radio and submillimeter observations may reveal jets or outflows associated with growing black holes. Upcoming surveys with the Nancy Grace Roman Space Telescope and the Square Kilometer Array will increase the sample size and provide statistical context. Finally, determining how long the little red dot phase lasts will be key. If it's brief, this would explain why these objects are rare at later cosmic times. Pinning down that timeline will help refine galaxy formation models and clarify how quickly black holes can emerge from dense stellar environments. The little red dots observed by James Webb Space Telescope are likely a transitional stage between dense star-forming galaxies and the first massive black holes. Their short-lived nature explains why we only see them at early cosmic times. These compact objects may hold the missing link to understanding how galaxies and black holes co-evolved in the young universe.